In this video, we will have a look at the Python implementation of ARIMA. We start by importing the necessary libraries and load the df.csv file. This dataset contains records of all the bank transactions over a period of 6 years. For this task, we club all the transactions month-wise and consider the total amount of transaction in that month for forecasting. You can see how our data looks here. We now move to the first step of ARIMA, making the data stationary. Different techniques can be used to make the data stationary, like taking a natural log and differencing. Here, we have a look at the different stages of differencing the original data. But first, we need to check if the data is stationary or not. The augmented Dickey-Fuller test is used to check the stationarity of data. We have the ADF check function, which returns a p-value. For the data to be stationary, the p-value should be less than 0.05. We now pass our data in the ADF check function to check for the stationarity. First time we pass the tf.value.dropNA, removing the NaN values, into the ADF check function. The plot we get is somewhat like this, and the p-value we get is 0.71, which is clearly above 0.05. Hence, this data is not stationary as of now. Taking the log of the values of data is considered to be the first and the basic step of differencing. Hence, we now take the log of all the values of the data and pass it to check if the new values are stationary. But we get the p-value to be 0.76, which shows that the data is still not stationary. Hence, we need to move on to the further step. We use the .diff function to perform the first order differencing. We pass this new data in the ADF check function to check for the stationarity. But we get a value of 0.63, which suggests that the data is still not stationary. But looking at the graph, we can see that there is some seasonality present in the data. That is, patterns are repeating over time. So, to remove this stationarity in data, we use the .diff12 function. We pass the new data in the ADF check function and we get this type of plot and a p-value of 7.8 into 10 to the power minus 6, which is clearly less than 0.05. Hence, we can conclude that our data is stationary. We have our difference data stored in the df testing variable. On this data, we now plot the ACF and the PACF plots to get the value of P and Q. The ACF gives us the value of Q. From the graph, we can observe that the first time a point is inside the blue band is at Q equals to 3. Hence, the Q will be 3. And the first time in the PACF graph, the value inside the blue band is the second one. So, P here will be 2. We move to the step 2 of ARIMA, that is, fitting the AR model. In the AR function, we perform a linear regression on the values before the current time step. That is, we take p values before the current value and perform linear regression on it. Here yt is some coefficient into yt minus 1, some other coefficient into yt minus 2, and such coefficients into the yt minus p, plus some error and some constant. Now let's have a look at our implementation of the AR function. We first take a value p and the data as input. dftemp is the copy of the data. We shift the data to get the previous p timestamp values, define a train size, split the data into train and test data. We then drop the NaN values from the data and reshape it to convert it into a format where the p previous values are in the list. We then perform linear regression to find the coefficients on the x train and y train data. Theta and intercept are the coefficients. We then predict the values using these coefficients generated through the LR for both train and test datasets and return the datasets. Using this AR function, we perform auto-regression on the dataset by taking the value of P as M. M here is a value considerably higher than P and Q. This hypothesis was put forward in the Hannan-Rissanen algorithm. This often involves testing and considering higher orders to capture potentially more intricate patterns or dependencies within the data. We take the value of m equals to 5 here and pass the dataset into this function. We get dftrain and dftest, which are the updated data frames having predicted values. dfc is a concatenated data frame. Now our next step is to get residuals, which are to be fed for MA. We get the residuals of the given value, which are later used in integrating MA and getting the test set predictions. The residuals here are calculated from df.c.value minus df.c.predicted value. And this is the density plot of the residuals. The residuals here look like white noise. From this density plot of residuals, we can clearly observe that most of the residuals are quite close to zero. Hence, our AR model is working well and we are good to go. Let's move to the step 3, integrating MA. The MA model or moving averages model uses the past forecast errors instead of values in a regression-like model. This is the equation where ET minus 1, ET minus 2 are the errors and theta 1, theta 2 and theta q are the coefficients. We use the below equation for the next function, where previous values as well as previous errors are concatenated and regressed. Hence, in our implementation, in this function, this is the ARMA integration function, where both the previous values as well as the previous errors are used and regressed together to get the final equation. Now let's dive into the ARMA integration function. This function takes P, Q, residuals, and the difference data as inputs. dftemp is a copy of the difference data without NaN values. We perform the shifting of the data to get the past P input values and the past Q residual values. We then define a train size and split the input data and residuals into the train and test sets here. We then clean the data frames by removing the NaN values, if any. We calculate the difference, take the relevant previous values for prediction. This is done just to make sure that the correct past values are taken. We then combine x and y having the last p input values and last q residual values to create combined x and combined y. After getting this combined x and y, we perform linear regression on these concatenated inputs and generate the intercepts and coefficients that are to be used for prediction. We then combine the test dataset for the last p input values and the q residuals like we did for the trained dataset, and we calculate the predictions on the test set by multiplying the values and the regression coefficients. After getting the predicted values, we calculate the RMSE on those predictions and print the RMSE and return the residuals. Now, we use this ARMA integration function to get the predictions. We pass P equals to 2 and Q equals to 3, which we got from the PACF and the ACF plots earlier. We also pass the residuals data frame and the input data frame. The RMSE is observed to be 0.043, which is pretty good. We then concatenate the residual train and residual test, which has the predicted values in it, and print the predicted value for the last 7 entries, which happens to be our test set. We now update df underscore c with the predicted values we got from res underscore c. Now we plot the original and the predicted values. This plot shows the input data in blue and the predicted in orange. We can see that our model predicts the data almost correctly. This is the magnified view of the test set. We can see that there is a very little difference between the two. Our next and the last step in ARIMA is to get back the original data. Remember, we difference the data multiple times in the beginning. Now we perform reversing steps of the differencing to check that the first column is the same even after reversing. These are the steps for reversing. We shifted by 12 because we differentiated by 12. We then shifted by 1 because we performed the dot diff. And we take the exponent because we took the log earlier. We perform the same operations on the predicted values as well. Now that we have our original data back, let's check how our predictions look like. We can see that our predictions are pretty close to the original data as well. This is the magnified view. Hence, we conclude that our ARIMA predicts the test set almost correctly with an RMSE of 0.043.